All right, guys, so today we are talking about transcendental functions, or in other words, things like natural logs. We'll be doing some trig functions. We're going to be working with e to the x, some of those different rules. So just a quick, some integration rules that you need to be aware of. If I'm taking the integral of 1 over x dx, well, if I think back to what gives me a derivative of 1 over x, and that was when you started with natural log of x, you ended up with 1 over x. So going backwards, if I start with 1 over x and I'm integrating, going backwards, then I end up with natural log of x plus c, with one minor difference, and that's the absolute value. Remember that the domain of our natural log function goes from 0 to infinity. Okay, so that's why we put the absolute value bar around the x, is we can't have negative values in there, or I guess the result of what is in there can't be negative. It has to be a positive. If I have the integral of 1 over u du, then again, it's just natural log of u plus c. And this is the big one. If I have u on the bottom and u prime is on the top, then I have the natural log of u. So if I have something like x to the fourth on the bottom, and I have 3x cubed on top, when I integrate, I end up with the natural log of x to the fourth. Okay, so just like the derivative of natural log is u prime over u, well, going backwards, if I start with u prime, I work my way backwards. So a couple of guidelines with these integrals. First of all, memorize the basic integration formulas. Second, find the formula that resembles part of what you're looking at. It's not always going to resemble it exactly, but that'll help you choose something that you can use for your u substitution. And if you can't find a u substitution, then try altering the integrand. So some examples we're going to go through. If I take the integral of 5 over x, that looks a lot like that natural log of x. The only problem is, if I were to take the derivative of x, I would end up with 1. And I don't end up with 1, I end up with 5. So there's a couple of ways that we can do this one. First of all, that's just a constant, so that 5 can move out in front. And now I just have 5 times the integral of 1 over x dx, which looks exactly like my natural log. So I can say 5 natural log of the absolute value of x, and then don't forget your plus c. And that's a 5 out in front, not a s. Who's writing those 5s? Those don't look like 5s. Okay, the second one, same idea. This looks kind of like my u prime over u. I don't just have an x on the bottom, I've got a function. But there's a couple of different ways that we can do this. The first way that we can do this is set u equal to 5x minus 1, which means that du, my derivative, equals 5 dx. Now, when I look at this function, I don't have a 5 dx. First of all, this 2, I can move it out in front. I can rewrite this as 2 integral 1 over 5x minus 1 dx. So I've got the dx, I've got the 5x minus 1. Now I've just got to move my 5 over like we always do. 1/5 du equals dx. So when I plug this in, that 1/5 can go to the front. I still have the 2 in front. Integral of 1 over u du. So now when I integrate, this becomes 2/5, and I want that u, I'm going to change that up to be u to the negative 1. Are we still there? Oh, we're frozen. Okay, we're going to shortcut. We don't need to do the long way anymore. I've got my 1 over u, that just looks like my natural log, right? So this is just 2/5, and then that becomes the natural log of u plus c. My only problem is I can't just leave it as u because this is an indefinite integral. So I've got to plug my 5x minus 1 back in. So I'm going to get 2/5 natural log of the absolute value of 5x minus 1 plus c. And that's where I'm going to leave my final answer, okay? Let's keep going. 10x minus 1 over 5x squared minus x. Now, if I take the derivative of this, I get 10x. And if I take the derivative of this, I get -1. So that means the top is just the derivative of the bottom. So my shortcut just tells me that the integral of u prime over u is natural log of u. So that becomes natural log 5x squared minus x plus c. Don't forget about the plus c, okay? Now this one over here on the right. All right, x squared plus 1 over x cubed plus 3x. If I look at taking the derivative of the bottom, I get 2x squared plus 3, and that doesn't look much like what I have on top. I mean, there's some similarities, but the numbers are quite a bit different. So I'm going to go ahead and start with a u substitution. So I'm going to say u equals x cubed plus 3x, which means that du is equal to 3x squared plus 3. Oh, dx. Don't forget the dx. Now, this takes care of my bottom, right? But now I need to try and make this look like the top. And the top has x squared plus 1, but mine has 3x squared plus 3. So I'm going to change this du. I'm going to factor out the 3 so that I have an x squared plus 1 left over. Now it looks more like, this just looks like the top. So I've just got to move the 3 to the other side. So that's 1/3 du is equal to x squared plus 1 dx. Now I can go ahead and substitute everything in. So my 1/3 goes out in the front, and integral. On top, I'm not left with anything because it all got wrapped up in my du. So I just have 1 over u du left on the top, which it looks like my natural log. So I've got 1/3 natural log absolute value of u plus c. But now I've got to plug my u back in from up here. So 1/3 natural log of x cubed plus 3x plus c. And I'm okay with that answer. That looks good to me. So moving on, let's try some fun ones. This one, the integral of x cubed plus 3x squared plus x plus 1, all divided by x cubed plus x dx. So back when our third hint was, if you can't find a u substitution, try to alter the integrand. That kind of is what this problem is wanting you to do. It wants you to try and change this part, the integrand, to make it look like something that we can work with. And the hint on this one is to do long division, which some of you are pretty good at. Some of you are pretty good at doing that synthetic, that long division stuff. And maybe that's something that we can go over in class. But I'm going to break this one up a little bit different. Okay, when I look at this problem, I see an x cubed on the bottom and the top. I also see an x on the bottom and the top. So I'm going to rewrite this. I'm going to rewrite this as x cubed plus x plus 3x squared plus 1, all divided by x cubed plus x. Now the reason I'm rewriting it that way is I want to split this up into two different fractions. So I'm going to split this up as x cubed plus x over x cubed plus x. Basically, I'm taking this part, and then I'm going to take this part as my other fraction, okay? Then I'm going to add 3x squared plus 1 over x cubed plus x dx. And this first part just becomes 1, so I get 1 plus 3x squared plus 1 over x cubed plus x dx. Now again, my hint to do that, going clear back here to the beginning of the problem, the reason I wanted to try splitting it up is because part of the bottom matches part of the top. And since everything's being added together, I can split it up into different fractions. So now I need to, now we got to do some extra work, right? Other than, actually we don't, because what this right here is a u prime over u. If I take the derivative of the bottom, I get 3x squared plus 1, which is exactly what's on top. So that just becomes a u prime over u. So when I integrate, the integral of 1 is just x. The integral of this part just becomes natural log of the absolute value of the bottom, x cubed plus x. And then don't forget a c. That's got to be there, guys. Don't forget that c. If you want to see the long division method, we can talk about that in class. Bring that up, and we can work through that one together. But if you can split up the top, why do the division? Because you're just going to end up with the same answer. Okay. This second one, I've got an x on top. I got an x plus 1 squared on the bottom. This doesn't look like I'm going to be able to cancel anything out. So I'm going to go ahead and I'm just going to start with a u substitution. So let's say u equals x plus 1. That means du equals just dx, because that x goes to a 1. So du is equal to dx. Now the problem is I've got this part and I've got this part, but I still have this x hanging out on top. The nice thing is when it's just an x, remember back in the last unit, I can take this equation, and if I solve it for x, if I minus 1 from both sides, x equals u minus 1. I can plug all of these things in and replace everything on the original problem. So I replace the x gets replaced with u minus 1, and I replace the bottom with u squared, and I end up with a du. Now, just like we did over here, I'm going to split it up. The integral of u over u squared minus 1 over u squared du, because u over u squared just becomes the integral of 1 over u minus 1 over u squared du. And now all I'm left with is my natural log stuff, right? 1 over u, that just becomes the natural log of u. The 1 over u squared, remember u squared is u to the negative 2. So that becomes u to the negative 1, and then I've got a times by the reciprocal, which is just a negative 1. And then I add c, so I end up with natural log of u plus 1 over u. Those combine to make a plus. This moves to the bottom, so I get 1 over u plus c. Now I got to replace my u's, right? Natural log, absolute value. My u is x plus 1 plus 1 over x plus 1 plus c. And I'm okay with that answer right there. That looks good enough for me. I'm not going to worry about trying to get rid of a fraction and making a big convoluted mess. We're just going to leave it right where it is. Okay. Integrals of the 6 basic trig functions. So we haven't done a lot of integrals with trig. We've done a little bit, but we've skipped some big ones like tangent. Look at this. The integral of tangent is negative natural log of the absolute value of cosine of u. The integral of secant is natural log of secant u plus tangent u. So all of a sudden we've got these transcendental problems coming in here. We've got natural log involved. And again, we're not going to go through why the tangent is what it is. That's something that we can get into in a little bit more in class at some point. We're going to focus on using these derivatives to do some math. So evaluate 0 to pi fourths of the root 1 plus cotangent squared x dx. Now, if I look up here, I see cotangent, but I don't see cotangent squared, and nothing results in 1 plus a cotangent of anything. So the way it's written now, I don't really have anything pretty. And if I were to do u equals 1 plus cotangent squared of x, the derivative of cotangent's not a very nice number either. So I don't know if that's going to be my best method. I'm going to try to rewrite the integrand. In other words, I'm going to try to change that 1 plus 1 plus the cotangent squared of x. I'm going to try and change that to something that I can work with that looks a little bit better. So going back to my Pythagorean identities, remember we have cosine squared plus sine squared equals 1. We also had one that we used last semester. 1 plus the cotangent squared of x is equal to the cosecant squared of x. So this is the one I'm interested in, because rather than 1 plus cotangent, I'd much rather just work with cosecant. So I'm going to rewrite this 0 to pi fourths of the square root of the cosecant squared of x. We okay so far? Now from there, I've got a square on the inside, and this is one thing that we forget a lot of times. This cosecant squared, what that means is the square root of the cosecant of x squared. So now I have a square root and a square canceling each other out. So I end up with 0 to pi fourths of cosecant x dx. Don't forget the dx's. I forget them all the time. Let's try to remember that they're there. Now this looks like one of my problems right here, right? The integral of cosecant is just negative natural log of cosecant u, so cosecant x plus cotangent x plus c. But this one, I actually have limits on my integral. So when I do that, instead of a plus c, I'm going from 0 to pi fourths. So I don't need to worry about my plus c. What I need to do is plug in pi fourths and plug in 0, which is where this one gets fun. So negative natural log of the cosecant of pi fourths plus the cotangent of pi fourths minus the negative natural log of the cosecant of 0 plus the cotangent of 0 and I think that's finally the end of, yeah, okay. So simplifying things a little bit. Here on the left, negative natural log, that's going to stay where it is. Cosecant, remember cosecant is 1 over sine, and cotangent is sine over cosine, okay? So this can be written as the negative natural log, the absolute value, cosecant of pi fourths is just 1 over the sine of pi fourths. So 1's going to go on top. And if I look at my unit circle, sine of pi fourths is root 2 over 2. Plus the cotangent of pi fourths. Well, that's easy. The cotangent, the sine at pi fourths is root 2 over 2. And so is the cosine, root 2 over 2. So the cotangent at pi fourths is just 1. And then I'm going to add the natural log, cosecant of 0. Now remember, cosecant is 1 over the sine. Now, sine of 0 is 0. So this ends up 1 over 0. That's not good. That means this is undefined. And it doesn't matter what else is going on. This part is undefined, which means my entire problem, all that work to find out that our entire problem is undefined. So let's double check and make sure on our calculator. If I were to get something like that, I would want to make sure that I didn't make an error doing my math. So get me out of here. Let's go math integral. I want to check this on my calculator. I'm going to go from 0 to pi fourths. And my original function is the second square root of 1 plus the cotangent. Remember, cotangent is 1 over tangent, which means my sine over cosine is going to flip over. So instead of sine over cosine, it's going to be cosine of x. Why is this not writing anymore? Oh, because I forgot to enter that. Cosine of x on the top. And why didn't it give me my... Okay, hold on. Delete, 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 delete. Okay, 1 plus alpha y equals, give me a fraction. There we go. Cosine of x over the sine of x. Nope, not the tangent. Delete. Sine of x. And then don't forget that whole thing that we just put in, it's the cotangent squared. So that whole thing right there needs to be squared. And I think that's everything, right? So if I hit enter, I get an overflow error, which means it's dealing with something that doesn't work. So undefined is a great answer for this one. I didn't make any mathematical mistakes, which is good because I don't want to re-record this video. I like doing things the right way. We'll save our mistakes for later because I'm sure there'll be one. Integration rules for exponential functions. So the integral of e to the x dx is awesome because it's just e to the x. The integral of e to the u du is just e to the u plus c. Okay, so if I'm evaluating my integral of e to the 4x plus 2, now I'm going to let u equal 4x plus 2. And I'm trying to decide where are we going to do these? These problems are all smushed together. So let's bring this one over here for now. So let's let u equal 4x plus 2. Then that means that du equals 4 dx. Now I don't have a 4, so I'm going to change this to 1/4 du is equal to dx. So when I plug everything in, when I replace it, I'm going to end up with the 1/4 the integral of e to the u du. And the integral of e to the u is just e to the u. So I end up with 1/4 e to the u plus c. And then I have to plug back in my u value. So 1/4 e raised to the 4x plus 2 plus c would be my final answer. Okay. Now to find, let's see. This one should be a relatively small one. So we're gonna do this one in red, and we're gonna actually bring it right up here. So I've got 6x e to the negative x squared, which looks a little bit scary to start with, but let's let u equal negative x squared. Okay, well that means that du is going to equal negative 2x dx. Now when I look at this problem, I don't have a negative 2. I do have an x and I do have a dx, so I just want to move the negative 2 to the other side. So I'm going to get negative 1/2 du equals x dx. So now I can plug this all in to my original integral. So when I plug that in, now originally I had this 6 in front. I'm going to go ahead and put the 6 in front. But then I've got to multiply by the negative 1/2. And then instead of the x, that just gets wrapped up in my du. So really I just have an e to the u. That's all that's in there. Right? I'm not missing anything. So the integral of e to the u was that nice one, but in front I'm going to have a -3, and then my integral is just e to the u plus c. So when I plug in my u, I get -3 e. My u was -x squared plus c. So it did it. That looked really this. I mean, we had all kinds of stuff. We had a 6, we had an x, we had a -x squared, we had an e. That one turns out to be a pretty easy u substitution if you know how to integrate e to the u. All right. Okay, so next one. We're going to do this one in red as well. We'll drop it over here. So the integral of 2e to the 1 over x divided by x squared dx. Okay. Let's start with u equals 1 over x and see what happens. That means the derivative of 1 over x, if you haven't memorized this one yet, it's x to the -2. Actually, it's not. It's -x to the -2 dx, right? Because I move this to the top, it becomes x to the -1, so I times the -1 in front, which gives me a -1 right there. Now, I do have, I actually have an x to the -2 right there. Remember, this can be written, du can be written as -1 over x squared dx. So the only thing that is messing me up right now is this -1. So I'm going to go ahead and move that to the other side and times by -1. So negative du equals 1 over x squared dx. Now that looks a lot better. So if I go back to my original integral, back to the start, I had this 2. I'm going to move that out front. Integral, the e to the 1 over x just becomes e to the u. And the x squared on the bottom gets wrapped up right here. So this ends up with a du. And then out in front, I need to remember to put that negative that came with my du, because I had a negative du. So my integral becomes -2 e to the u plus c, which is -2 e to the, my u was what? 1 over x plus c. So just -2 e to the 1 over x plus c. So this is one of those times that the e to the x actually made the problem nicer because we're going backwards. You know how it usually gets uglier when we're taking derivatives? Well, we're going backwards. So this one's actually making mine look a little bit nicer. Okay, we are taking a lot of time on these problems. I think it's probably okay though. Let's look at this one. 3 sine of x e to the cosine of x. You know what? I'm going to start with u equals cosine of x, because then du is equal to the negative sine of x dx. So I see a sine of x. I see a cosine up here. The only thing I don't see is the negative. So negative du equals sine of x dx. So when I plug this in, that 3 I'm going to move out in front. The negative I'm going to put in front. The rest just becomes e to the u du. And that's really it. Wow. Okay. So -3. I keep going to do natural log because I've been doing a lot of those. -3 e to the u plus c becomes -3 e to the cosine of x plus c. And that's going to be my final answer. Okay. All right. Now what do we got? Use your calculators to help find the following. Let f of x be an antiderivative of e to the x squared. That says e raised to the x squared. If f of -1 is 2, find f of -2. Okay, so let's set this up. I don't know if we'll do all the calculator part, but let's at least get it set up. So it tells me that big F of x is equal to the antiderivative, which is the integral of e to the x squared. So big F of x equals the integral of e to the x squared dx. Now, it gives me endpoints. It doesn't look like it does, but it does. It gives me -1 and it gives me -2. So I can actually plug in, if I am going to be integrating, I'm going to put the -2 on the bottom, I'm going to put the -1 on top, and I'm integrating e to the x squared dx. Now here's why I want to do that. Because fundamental theorem of calculus tells me that I can take big F of the top, which is -1, and if I minus big F of the bottom, -2, I'm going to get this integral. Right? Now this looks like an AP question that we just did on the test a couple weeks ago. So big F minus big F is equal to that integral. Now, if without a calculator, I'm out of luck. I'm in a lot of trouble. But it told me to use my calculator. So the first thing I'm going to do, I'm going to put this in the calculator. -2 to -1 of e to the x squared. So if I go to my calculator and I'm going to do, let's see, clear out of this math integral, I'm going from -2 to -1. And my integral, what was I doing? Second e raised to the x squared dx, right? Okay, so that value is 14.989976. Wow, that's a mouthful. 14.989976. So this is equal to 14.989976. And over here, I have f of -1 minus big F of -2. Because f up here, it told me that f is the derivative, the antiderivative of the other side. So I can use that fundamental theory of calculus. All right, well, it also told me that f of -1 is 2. So 2 minus f of -2 equals 14.989976. So now if what do I want to do? Add -2 from both sides. So negative f of -2 equals 12.989976-ish. And then to get the answer, I just have to multiply by a -1. So big F of -2 is going to equal negative 12.989976. And that's a mouthful. And that's probably more than enough for one video. So on your homework, if you want to start trying the worksheet or the Delta Math for 5.1, if you watch this over the break, if you want to work on those over the break and get a head start, great. We will go over the questions. We'll talk about this a little bit more your first day back from Christmas break. We'll dive into this. We'll work on homework questions as well as Delta Math in class.